Alright, we're going to look at numbers in a little bit more detail. So the real numbers. And now we're going back a few years. We're going to talk about prime factors. So the building blocks of our numbers. So every number can be broken down to its prime factors. So let's have a look at a little example. There's 324, which of course is 4 times 81, but we can keep going. So 2 squared times 3 to the power of 4. There's the building blocks that make up 324. Now, whether you realised it or not, when you're factorising algebra, that's exactly what you're doing. You're breaking it down to, well, not its prime factors, but all of the factors of that particular unknown. So highest common factor. So that's where we're looking for the biggest number that goes into 2 other numbers. So what we do is we write down both numbers in terms of the prime factors. Then we would pull out all the common factors. So let's do an example. So 1,176, which is 6 times 196, so I can keep going. 3 times 2 times 49 times 4. So we can get 3 times 2 cubed times 7 squared. 252 is 4 63s. 4 times 9 times 7. So we get 2 squared, 3 squared, and 7. So there are some common factors there. So the highest common factor would then be 2 squared times 3 times 7, which turns out to be 84. In algebra, that's the same as what? Yeah, it's exactly that. There was no big trick there. Factorising, when we pull out the highest common factor, so things like when we pull out highest common factor in algebra, we always pull out the lowest power, I guess is what I was getting at. And that was the same here with highest. To work out the highest common factor, we pull out the lowest power. So with the 2's, we had 2 cubed and we had 2 squared, we pulled out the lower power, the 2 squared. So it's the same skill. Then there's another skill we use with those prime factors is finding a lowest common multiple of 2 numbers. So this time it's the smallest number that both numbers go into. It's alright, again you'd start off by writing it, but this time you write down all the factors without repeating. So let's make a simpler one. We'll pick a couple of small numbers, 48 and 15. So 48, 16 times 3, which gives me 2 to the power of 4 times 3. 15, 3 times 5, and that's the best I can do. So the lowest common multiple, 2 to the power of 4 times 3 times 5, turns out to be 240. Where do we do that in algebra? Yes, it's the algebraic fractions when we're adding or subtracting, and we want to get that lowest common, what we call it a denominator in that case. But that's exactly the same thing. We write down, remember I said if it's not there, put it down. So same idea. So I guess what I'm getting at is algebra, the skills we often use in algebra are exactly the same as the skills we use with normal numbers anyway. Sometimes disguised and it looks like it's something else, but really no different. Okay. Another thing that comes in handy are divisibility tests, especially when you are factorising algebra. Say it's a quadratic and you're saying, oh, I want 2 things that multiply together to give. So does this divide into it? Things like that. Some of these, of course, are easy. Some of these are hard. Let's see if we can remember our divisibility tests. If you get in quick, you can get the easy ones. How do you know if a number is divisible by 2? Okay. Yeah, it's an even number. Okay, right. 3.
Add all the digits.
Right. So if you were to sum all the digits, that would also make a number that's divisible by 3. 4. Yeah, the key with that one's the last 2 digits. So last 2 digits are divisible by 4. Oh, here's an easy one. 5? Right. Ends in 0 or 5. 6.
Even and when you add them.
Yeah, I mean, this is one where we sort of combine the divisibility test for 2 and 3. So it's divisible by 2 and 3. So in other words, you've got an even number where all the digits add up to a multiple of 3. Now, if you know 7 without looking at the sheet, I'm going to be impressed. 7, anyone? Yes, it's quite an interesting one. Double the last digit and subtract from the other digits, and then the answer will be divisible by 7. Back to an easier one now. 8. Right, it's to do with the last 3 digits, divisible by 8. 9. Right. This time it's, well, sort of the same as 3, but you're applying it twice, I suppose you could think of it, because 9 being 3 squared. So some of the digits is divisible by 9. So similar to that. Okay, 10. Okay. Ends in a 0. 11's another interesting one. A bit more commonly known than the 7 one, but anyone? Yeah, even digits, what about them? Right, so you're looking at the sum of the even digits and the sum of the odd digits. The sum will be or differ by a multiple of 11. Okay, so if you add up all the numbers in the odd position, you add up all the numbers in the even position, the difference should be divisible by 11. Do we want to do an example of that one, or are we clear on that? See, that's the problem with calculators, you know. It's caused us to forget all these fun little tricks and what have you. People get lazy. All right, I'll stop there. I mean, there are tests for 12 and 13 and so on. You can, I'm sure, search them out on the net if you're interested. Let's talk a bit about fractions and decimals. This is the way we express our numbers. Now, converting a fraction into a decimal is very easy because the fraction bar is just another symbol for division. So numerator divided by denominator, bang, you get your answer. Converting decimals into fractions, going back the other way. Well, if it's a terminating decimal, the nature of our number system makes that very easy because we have a decimal number system, and if the number stops, then we know it's so many tenths, so many hundredths, so many thousandths, however. But of course, if it doesn't stop, we've got 2 possibilities. One possibility is that there is no pattern to it. And that's what we of course call an irrational number. Well, we can't write those as fractions. They're impossible. Because as soon as you can write a number as a fraction, you know its exact value. And we don't know the exact value of irrational numbers. But the ones that recur, a pattern happens. Now, there is a method which I shall show you, and you've probably seen. And then I'll tell you to ignore it and show you the sensible way of doing it. Okay, so 0.6 repeater, I've deliberately picked one that we know the answer to. So we go, let's pretend we don't. Okay, well we know it's 0.66666666, and it goes on, there's our pattern. So I'll let x equal 0.6 repeater. And for those that are catching on to this, that means x is 0.66666666, and so on. Now basically I want to get rid of this repeating part because I want to come up with something definite. So what I do is multiply it by 10. Move the decimal point 1 place, and I get 6.66666666. Now, whilst those 6's are going on forever, they're going on forever in both numbers, so I can subtract. And when I subtract, I'll just be left with 9x is 6. And now I've got something definite that I can work with. X, therefore, is 6 on 9. There's our fraction, because we said 0.6 repeater was x. 6/9, which is, of course, 2/3. All right. Let's do it when 2 numbers are repeating. So 0.81 repeater. And for those who are a little bit unsure, that means 0.818181818181818181818181, and it goes on forever. So all right, we'll do the same idea. X is 0.8181818181. I'm not going to multiply by 10 because I won't get 818181818181. I'll get 1818181818181818. No good to me. So we'll multiply by 100, and then I get 81.818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818181818 81, 81, 81, 81, 81, 81, 81. The 8 ones disappear, and we have a definite answer now. So 81 on 99, 9 on 11. Okay, let's try one where not all the numbers are repeating. So we've got 0.327, but the 27's repeating, so of course this means 0.3. 27, 27, 27, 27, 27, 27, 27, 27, 27, 27, and so on. Okay, we'll do it the same way. Let x be that. Now, if I multiply by 10, remember I'm trying to get the same number underneath it so I can cancel it. If I multiply by 10, not going to work because I'll get 3.27272727. No good. But if I go 100, it will line up. So effectively is however many numbers are repeating, that power of 10, that's what I'm going to multiply by. One number repeating, I'll multiply by 10 to the power of 1. Two numbers repeating, multiply by 10 to the power of 2, and so on and so on and so on. Because when I do my subtraction here, I get something that we don't like, because I'll end up with 32.4 on 99, which of course, that's just a stupid answer. Why is it a stupid answer? Because there are two ways of writing numbers. Decimal notation or as a fraction. You don't mix the two. It's stupid. So we would multiply top and bottom by 10 and we get 324 on 990, which turns out to be 18 on 55. The correct way of writing recurring decimals, if I had three numbers repeating, I wouldn't put 3 dots. You just put 1 dot at the first number of the pattern and then a second dot at the last number of the pattern. That's all we do. Now I said I'm going to show you this method and then go, forget it, what a waste of time. Because maths is about finding patterns and using them to our advantage. And so here's how we should do it. Because we should just look at it, and even pretending we don't know the answer, we should be able to look at it and go, oh, this is what it is. 0.6 repeater. I know on the top of the fraction it'll be 6 because 6 is the number that's repeating. I know 9 will go on the bottom of the fraction because there is one number repeating, so I'll write 1 9 down. 6 over 9, 2/3. 0.1 repeater therefore is 1/9. 2 repeater, 2/9. 3 repeater, 3/9. This same idea then. 0.81 repeater. Oh well, 81 will go on top because that's the number that's repeating. On the bottom, one number repeating, so I'm going to use 2 9s. Now when I say 2 9s, I don't mean 18. I'm going to physically write 2 9s. 9 9 is 99. So 81 repeater, 81 on 99. 0.72 repeater, 72 on 99, and so on and so on and so on. 9 on 11. So if I now gave you this one where there's 4 numbers repeating, and perhaps when we walked in today you'd go, oh my God, what on earth is that? Now it's a piece of cake. What is it? Yeah, 7134 and 9999. There's your answer. Okay. Now does that simplify down? Yeah, it does. Of course it does. Of course. Top number is divisible by 3. Did some of the digits, 3. See, told you it was useful. Now, okay, but what about the ones where not all the numbers repeat? All right, 324 on the top. Why? 327 minus 3. I write down the numbers, but subtract the number that's not repeating. So I'm writing 327 down and I'm subtracting the 3 because it's not repeating. How do I handle the bottom? 2 numbers are repeating, so I write down 2 9s. One number is not, so I write down 1 0. And it makes sense to write that 0 at the end of the number, because if I was to put it at the front of the number, it does nothing to the number. So we always put it at the end. So 324 on 990. 88 on 55. So therefore, if I now get this one, 0.1096 repeater, but only the 9 and 6 are repeating, so 1096, 96, 96, 96, 96, it is now extremely quick to come up with the answer it's going to be 1,086, because that's 1,096 minus 10, on 9900. 2 numbers repeating, 2 nines. 2 numbers not repeating, 2 zeros. There's our answer, that's the fraction. That simplifies down to be 181,1650. Alright, whoop. Right.